Hello! Today we are going to deal with a very practical question. What is the pressure drop over a pipe that transports a liquid? The answer is obviously needed if you need to design the tube system, including its pump. Should you have a big or a small pump? On what does that depend? Take for instance the case of the Trans-Alaska pipeline that transports oil from the Arctic side of Alaska to its southern harbor Valdez. That is a pretty big pipeline, 800 miles long with a diameter of about 1 meter. Through this, oil is pumped at the flow rate of 1 million barrels a day. This oil has a viscosity of 3.5 times that of water. Any guess what the pressure drop over the entire pipe will be? 1 bar? 10 bar? 100 bar? 1,000 bar? More? We need to approach this systematically. So let's start with the most simple case, a straight cylindrical horizontal tube. A fluid is flowing through it with a mean velocity v sub x. The pipe has a length L and a diameter d. The question is, what is the pressure drop at steady state conditions? First thing we need to know, what causes this pressure drop? The answer is friction at the wall. That is caused by shear stress at the wall. We know what governs that. For a fluid like water or air, we have a simple relation between the shear stress and the velocity gradient. The stress from the wall on the fluid, that is the friction force per unit area, equals, according to Newton's action is minus reaction, minus the shear stress exerted by the fluid on the wall. And this is equal to minus the viscosity times the velocity gradient at the wall. Unfortunately, for most situations we cannot mathematically find the velocity gradient. But we have seen that before. We can still use dimensional analysis. So, we write the shear stress as a function of the governing parameters. These are the average velocity in the pipe. The faster the fluid flows, the higher the pressure drop. The pipe diameter, as we know that pumping the same flow rate through a narrow tube is much tougher than through a tube of large diameter. The liquid viscosity, as pumping syrup is more difficult than water. And finally the density. That one we can expect as pressure drop and momentum are related via the momentum balance. And there we saw that rho v is actually concentration of momentum. Next we write the units for each quantity and we raise the quantities on the right side to the power a, b, c and d. Then we make the equation dimensionally correct. So we get for the kilogram 1 is c plus d. For meters, minus 1 equals a plus b minus c minus 3d. And for seconds, minus 2 equals minus a minus c. This is one unknown more than we have equations. So we can express, for instance, a, b and d in c. That gives a equals 2 minus c, b equals minus c and d equals 1 minus c. Use this in the original expression for the stress at the wall and we find the wall shear stress, made dimensionless by rho v squared as a function of the Reynolds number. We write this in a slightly different form. The shear stress at the wall is minus F times half rho v squared. The reason is the same as we had with the drag force. A half rho v squared is one of the terms in Bernoulli's equation where it gets related to pressure. Note that F is thus a function of the Reynolds number. It's known as the Fanning friction factor, or the friction factor for short. Okay, we needed this because we were thinking about the pressure drop over a pipe. So here's our pipe again. The pressure drop over the control volume between the dashed lines can be found from a momentum balance. In steady state, this reads as 0 is in minus out plus production. The in and out term cancel each other, as you can check yourself. Thus all we need to do is find all forces acting on the fluid in the control volume. From the left there is a pressure force, P sub 1 times the cross-sectional area capital A of the tube. It works in the positive x direction. Similarly, at the right side there is a pressure force acting in the negative x direction, P sub 2 times capital A. Finally, we have the friction force from the wall on the fluid, working in the negative x direction, τ times the area of the wall of the pipe between point 1 and 2. For this area we write tube length times the wetted wall perimeter, and denote this by S times L. Now we can back out the pressure drop over the length L. P1 minus P2 equals minus τ times SL over capital A. For a cylindrical pipe we can easily find that SL over A is equal to 4 times the length over D. Now we will use our new formula for the wall shear stress and substitute everything in our delta P equation. P1 minus P2 equals 4L over D half rho V squared. This is our model for the pressure drop. All we need to have is data on the friction factor F. We'll come back to that in a second. But first, we can use this new expression in the mechanical energy balance. Remember that we had there the unknown dissipation term, the destruction of mechanical energy into heat via friction. We wrote this in a flow system as mass flow rate times dissipation per unit of mass. Now, for a steady state of flow in a horizontal pipe, that is Z1 equals Z2 with constant diameter, which means V1 equals V2, the mechanical energy balance states that the pressure drop divided by rho is equal to the dissipation per kilogram. Thus we find for the dissipation E sub Fr equals 4F L over D half V squared. There's one more thing we need to introduce to make our pressure drop relation more generic, the hydraulic diameter. It is defined as D sub H equals 4 times the cross-sectional area of the pipe divided by the wetted perimeter. With that we can write our pressure drop relation as delta P equals 4 times L over D hydraulic times half rho V squared. With this hydraulic diameter we also redefine the Reynolds number as rho V times the hydraulic diameter over the viscosity. Experiments have shown that if the Reynolds number is higher than 10 to the 5th, the F curve is the same for many different shapes of pipe. Let's do an example. Suppose water was not flowing through a cylindrical pipe, but instead through an open rectangular channel. The channel has a height capital H and a width W. It is filled for a height small h with water. Question: what is the hydraulic diameter of this duct? Answer: by definition it's 4 times the cross-sectional area divided by the wetted perimeter. And here is a catch. The cross-sectional area is straightforward. It is W times small h. But S is a little more subtle. We call it the wetted perimeter and not just the perimeter. And that is for good reasons. Naively, one would say the perimeter S is twice small h plus twice W. But that's wrong. The top part is open. There is no wall causing friction. There is only air, which gives rise to hardly any friction. So the wetted perimeter is only 2 H plus 1 time W. Okay, we're almost done. All we need is an expression for the fanning friction factor, or a table or graph. But before we give that, let's first look at a nice analogy. Pressure drop in a pipe versus drag force on, say, a sphere. Look at both equations. They are quite alike. That's logical, because for the drag force we had an identical analysis with the same arguments. Both expressions have an empirical coefficient, the fanning friction factor and the drag coefficient. What can we, based on the analogy, expect for the fanning friction factor? F will be inversely proportional to the Reynolds number in the laminar regime and tends to become constant for high Reynolds number in the turbulent regime. And that's indeed the case. For laminar flow in a cylindrical pipe, we can derive 4F equals 64 over Reynolds, an exact solution of the momentum balance. For high Reynolds number, 4F indeed changes less and less with Reynolds. There's a nice empirical relation for 4F, Blasius law, which is 4F equals 0.316 over Reynolds to the power 1/4. This holds for pipe with smooth walls and for Reynolds in the range of 4,000 to 10 to the 5th. Note all the other lines in the graph. They give 4F for pipe with rough walls, where the friction is higher. This is given in terms of a relative roughness, which is the mean height of the roughness divided by the pipe diameter. Okay, now we are in the position to calculate the pressure drop over the Trans-Alaska pipeline. We're going to treat it as a straight horizontal pipe. The influence of bends is thus ignored. Our pipe is thus 800 miles long, or a little over 1300 kilometers, and has a diameter of 48 inch. Here are the calculation steps. First, we need to have the mean velocity in the pipe. That is obtained from the given volume flow rate. V equals phi sub f over pi over 4 d squared, which gives V is about 1.6 meters a second. From that we compute the Reynolds number, and that is needed to find the friction factor. Thus, in step 3, we use the fanning friction graph and read it for a smooth pipe at a Reynolds number of 4.7 times 10 to the power 5. This gives us for F a value of 0.003. Finally, in step 4, we compute the pressure drop as delta P is 4F L over D half rho V squared. The result is a delta P of 137 bar. Pretty big, but then again, this is a very long pipe. Okay, let's summarize today's lecture. We modeled the pressure drop over a straight pipe and found that the shear at the wall could be written as tau equals minus F times half rho V squared. With F, the fanning friction factor, which is a function of the Reynolds number and not a constant. Next, we made a steady state momentum balance which reduces to the sum of forces must be 0. This gave delta P equals 4F times L over D hydraulic times half rho V squared. The fanning friction factor can be found in graphs and tables. Finally, we also derived an expression for the until now unknown dissipation in the mechanical energy balance. E sub Fr equals 4F times L over D times half rho V squared. That's all for this lecture. Please make the exercises always starting with a sketch of your problem. Good luck, and see you at the next lecture.